A suspension bridge with weight uniformly distributed along its length has twin towers that extend 75 meters above the road surface and are 400 meters apart. The cables are parabolic in shape and are suspended from the tops of the towers. The cables touch the road surface at the center of the bridge. Find the height of the cables at a point 100 meters from the center. The first thing I'd like to do here is to draw a picture that's going to help me decipher the given information. We have a suspension bridge with twin towers that are 75 meters above the road surface and 400 meters apart. So the towers are 75 meters above the road surface and they're 400 meters apart. The cables are parabolic in shape, suspended from the tops of the towers, and they touch the road surface at the center of the bridge. So we've got cables suspended from the tops of the tower, parabolic in shape, and touching the road surface at the center of the bridge. Find the height of the cables at a point 100 meters from the center. If the total span of this bridge is 400 meters, from the center to the tower is a distance of 200 meters, and half of that is going to be the distance 100 meters that we're being asked to find. We want to determine the height of the cable, which is this distance here, at this point. So what we need to find is a function that represents the height. And ideally, that height function would depend on a distance x. And if x represented the distance from the center, we would be plugging in 100 for x. If we consider this parabola to be on the Cartesian plane, then that's precisely what x represents. The x value in question would be 100, and this height distance would be represented by the y value of this function. So what we need to find is essentially the equation of a parabola, and then plug 100 into it. And it's much easier to start with the equation of a parabola in vertex form, which, as a reminder, is f at x is equal to a times x minus h quantity squared plus k, where hk is the vertex point. So let's fit our scenario to this. We're going to call this h at x because it's representing height. We don't know what the value of a is. X is going to be part of the formula, but what we do know here is that the vertex is located at 0, 0. So our h value is 0 and our k value is also 0. So just plugging in the vertex gives us quite a boost. What we have is the quadratic function a times x squared, and all we really need to find now is the value of a, which, if we think about this from the perspective of transformations, that outside multiplier is a vertical stretch or compression, which affects the width of the parabola. In order to find that outside multiplier, we need another ordered pair that we can plug in for x and y so that we can solve for a. If we come back up to our concept drawing, we can see that basically we put the Cartesian plane right down the center of our parabola, and that means that this ordered pair up here has an x-coordinate of 200, because this distance is 200 here, and a y-coordinate that's 75, because that's the height of the tower. So we could plug in the ordered pair 200, 75, but we could also plug in the ordered pair negative 200, 75. Either one of these points would work. So let's plug in the y-coordinate 75 is equal to a times the x-coordinate, which is 200, and then solve for a. So we have 75 is equal to a times 40,000, which is 200 squared. And now we're going to divide both sides by that 40,000 to completely solve for a. And we get that a is equal to 0.001875. Now remember, this is the outside multiplier that was used in our function to give us the vertical, it looks like compression in this case, which now enables us to completely write our height function as 0.001875 times x squared. So let's come back to our concept drawing and remember, now that we have our height function, we can take the x-coordinate 100, plug that into the height function to get the corresponding output when the input is 100. And this output represents the y-coordinate of the ordered pair, but it also represents the height of the cable at this point. So we're evaluating the height at 100 using the function that we found. So let's plug 100 in and evaluate. We're going to have 0.001875 times 10,000, When we multiply by 10,000, we move the decimal to the right 4 places. And so the height of the cable is now 18.75 meters above the road surface.